It's with pleasure that I get to introduce BJ Fregly again. For those of you who may not remember, he was here a couple of years ago, and he will be presenting new stuff this time. He assures me that it's new. But BJ is a Knox T. Millsaps professor at the University of Florida. BJ did his PhD at Stanford a few years ago and did a postdoc in Lyon, and he's been working at the University of Florida since then, and is in the Department of Mechanical and Aerospace Engineering. BJ's primary interest in working in musculoskeletal modeling, and this is kind of the reason why we work together and have worked together on a few occasions. And BJ's work's been funded by NSF, NIH, all of the big acronyms you could think of in the United States. And of course you're going to find out why he's the recipient of those grants after this talk, because he does excellent work. And I was fortunate enough to be involved with a project with BJ called the Grand Knee Challenge, which he's kind of become well known for as well. And on last check, I actually just did a check before I came down, there has been over 7,000 downloads of that data set, which is an instrumented knee data set where actually with a colleague of ours at the Scripps Clinic in San Diego, we captured a data set of patients who had instrumented knees. And then we set about having a competition to see who could predict those forces. And it's been a very successful outcome, I think, and I believe that NIH would also believe that it's been a successful outcome from that project. And I was fortunate enough to be involved with BJ on that. So I'm going to finish there. I'm not going to take up any more of his time. But just thank you again for coming out here. He's come out here with his son Christopher. We made him do a lot of work over the last week and a bit. Nothing like using the coercion of a father to make your son do a whole bunch of experiments with us. But thanks for coming out here. I hope you've enjoyed your trips and travel around New Zealand so far, and hope that you'll come again after this one.
We'd love to. Yeah, thank you for the invitation. So I'm going to talk about computational neurorehabilitation of walking impairment. So what in the world does that mean? Well, let's start out by doing a little thought experiment. And so I want you to imagine that, and we're going to start on a high note here this afternoon. Imagine that you've had a stroke. By the way, 1 in 6 people, according to the World Stroke Organization, will have a stroke in their lifetime. So if you look around this room, I don't know, 30 or so people, that means roughly 5 of us are going to have a stroke at some point in our lifetime. So that's a pretty sobering thought. But for many people that have had a stroke, if this is you, your walking has become slow, labored, and inefficient. You can no longer do many of the things that you love to do. You can no longer keep up with your family and your friends. You can no longer exercise regularly to stay healthy. And of course, that's going to have some consequences. So you may develop heart disease and diabetes. And if statistics are accurate, you're going to die 7 years sooner than you would have otherwise. But stroke is not the only thing that has a significant impact on people's ability to walk. So in addition to stroke, we have common conditions such as osteoarthritis, typically of the hip or the knee. We have Parkinson's disease, frequently have the shuffling kind of gait, and cerebral palsy. So one of the things that you'll notice is that my screen just went blank. Excuse me for a second. I think it may have just realized that there are 2 displays here. No. Never had that happen before. Oh, no, PowerPoint crashed.
Oh, Microsoft.
Yeah, thank you, Bill Gates. Let's try that again. I've been playing with this for a while, and I have not had this crash ever. All right, back to where we were. All right, so the point I wanted to make here is there's a common factor in all of these conditions, in that these walking impairments really have an underlying neurological component. And so when we think of walking impairments, we shouldn't just think musculoskeletal, we need to think brain as well. And of course, the fact that the brain is involved makes them difficult to treat. So why should we care? I've already given you a little taste of that, but walking impairments are leading causes of long-term disability worldwide. They're extremely costly to society in terms of healthcare costs and lost productivity. They produce a significant decrease in quality of life and possibly independence as well. If you lose your ability to walk, the chances of needing to be moved out of your home into a care facility go up greatly. They increase the risk of serious health problems. So once you can't move around as much, your risk of heart disease, diabetes, stroke, and ultimately death increase a lot. I found this great picture here because once you lose your ability to walk and these other health conditions start, you can start to go down a slippery slope that's difficult to recover from. So you really don't want to start down this process. And then finally, walking impairments generally lack effective treatments for restoring as opposed to replacing lost function. So if you lose your ability to walk, a wheelchair is a great invention. It can get you around, but that's really not what we want ultimately. We want people to be able to ambulate on their own because then we get all the other health benefits as well. So, one other comment here. So many of us have a friend or family member who has a health condition that significantly impairs walking ability. So if I went around this room and asked you all, I bet most of you could identify a friend or family member who has arthritis, has had a stroke, or has some other condition that influences their walking ability. So why don't we have great treatments for improving walking ability? Why is this so challenging? Well, since I'm here in New Zealand, so I was talking to Christopher yesterday, and he was having lunch with some of the students here, and he said, Dad, everyone was talking about some boat race thing related to America. Okay, so that's the American perspective on the America's Cup. Of course, you guys all know this is Team New Zealand, and you're all very familiar with the America's Cup. And a little story that you may not be aware of, how many of you know who won America's Cup in 1995? Team New Zealand, all right? So how did they win America's Cup in 1995? And by the way, they were way outspent by many other countries, including the United States. So they were kind of an underdog that year. Well, the way that they won it is they used some state-of-the-art computational technology. So they designed their boat using computational modeling, and I actually worked for a software company whose software was being used by Team New Zealand. And what I heard was that every day, once they collected data from how they did that day, they'd put that into their computer models, run new optimizations, and predict what aspects of the boat they could tweak to try to get more speed out of the boat the next day. And it worked really well, and they won the America's Cup in 1995 as an underdog. So Team New Zealand won the 1995 America's Cup race by using design optimization technology, combining simulation with optimization to try to find a best design. So let's say that you wanted to win the America's Cup and you were going to enter a boat. Would you want to race in a boat designed solely based on experience? Oh yeah, I've done this before, I have a sense that this is kind of how I should do the boat design. Kind of like boats were designed in the early 1900s. Is that the sort of boat that you would want to race in if you wanted to win today? Certainly not, right? Well, guess what? The current treatment design process for walking impairments is like boat design for the America's Cup in the early 1900s. It's based mainly on experience. There's not a lot of computational technology and optimization that goes into the process. So the goal for my research is really to make the treatment design process for walking impairments like what Team New Zealand does today in their boat design process using design optimization technology. So the key question for my talk today is how can we use computational models to design more effective neurorehabilitation treatments for walking impairments? And this is what I call computational neurorehabilitation. So the computational part, because we're going to use computer models to simulate people. Neuro, it's going to be related to how the brain controls movement, so we're going to have some model of the brain. And then rehabilitation, we want to restore, rehabilitate lost function, in this case for walking. So my goal is to share my vision for how computational models can be used to design neurorehab treatments that are going to maximize recovery of lost walking function. And as I go through this lecture, I'm going to be emphasizing three key concepts that I want you to be aware of. The first one is the idea of predictive rather than descriptive analyses. So if you look at what we do in the musculoskeletal modeling world, a lot of what we do is what I would call descriptive. What happened when? So we go and we collect some data, and we can't measure everything that we want to measure. So using the data that we collect, we want to use our models to describe or suck out some other information from an existing data set. But where we want to go for treatment design is we want to move away from descriptive and move toward predictive analyses. What will happen if? What will happen if I change something about the way the person controls their motion? What will happen if I change some surgical parameters? So we need to be able to answer those what-if scenarios. Second, patient-specific rather than generic models. So most of what you'll find in the literature is that people are developing interesting walking models, but they tend to be simple, planar, stick figure sorts of things, and they're just of a generic individual. But if we want to design treatments that we're going to apply to individual patients, then the model needs to be customized to the patient. And finally, restoration rather than replacement of lost function. Okay, a wheelchair is good. Replacement of lost function is definitely valuable, but restoration is much better. We'd much rather get the person back to a normal ability to walk as much as possible. So the outline for my talk, I'm going to cover 4 points here. So the first point is, what challenges are present? Why aren't we able to do this yet? Next point, what ingredients are needed? What general paradigm do we need to follow if we want to get this to work? Third, what treatments have been designed already using patient-specific computational walking models? And then last, what directions should be pursued in the future if we want to make this approach a reality? So first, what challenges are present? We're going to look at 4 challenges. Everyone's unique. Lots of treatment options exist. Movement data don't provide the answer, and people change over time. So first, everyone's unique. So each person is different neurologically, right? Our brains control our movement in different ways. Physiologically, our muscles generate forces in different ways. And anatomically, some of us are bow-legged, some are knock-kneed, some are tall, some are short, right? All those differences are important. And so if we want to create computational walking models to predict treatment outcome, then we're going to need to account for these patient-specific neurological, physiological, and anatomical characteristics. And by the way, the Musculoskeletal Atlas project that Tor is working on here is a great way to address that anatomical bullet there. Many important model parameter values are not observable and cannot be measured experimentally. So this is a lot harder than designing a racing boat for Team New Zealand. When you design the boat, you know what all the properties are of the materials and structures that you're working with. Here we're trying to back calculate a model of a person that matches all of these different characteristics, and that's not an easy chore. So calibration of critical parameter values in a patient-specific computational walking model, it's just very difficult, and this is really one of the main holdups in our ability to develop treatments with walking models. As McMorland said, no 2 strokes are the same, and what that means is if you want to make walking models to figure out how to treat people that have had a stroke, each model of each patient is going to have to be different as well. Okay, lots of treatment options exist. Some of you may have seen the movie The Imitation Game. Really great movie. So it's about Alan Turing, who is a mathematics professor in England during World War II. And he's trying to crack the German Enigma code. And the problem was that the code would turn over every 24 hours. And so if they couldn't crack it in 24 hours, the window of opportunity was gone, and boom, a new code was there for the next day. And the interesting thing is Turing knew that there was a solution there, right? He knew there was a key to crack the code, and he just couldn't try all the options fast enough to figure out how to crack it. And so he basically designed the first computer to figure out how to crack the code. And so we're going to make a similar premise for designing treatments for walking impairments. There is a solution out there. There's a solution that exists. We just have to find a way to find it. So what is that solution going to involve? It's going to involve a treatment prescription. Out of all the possible treatments in the world, which treatment or combination of treatments will produce the best possible functional outcome? It could be that if you take 2 typically separate treatments and you combine them together, maybe there'll be a synergistic effect, but it would be really hard to find that clinically. You just can't try all the possibilities clinically. That's what we want to do with computational models. And second is treatment dosage. For the selected prescription, how much of the treatment should be given to produce the best possible functional outcome? So just like with the prescription drug, if you give too little, it might not be effective. If you give too much, then it could be dangerous. So we have to get the dosage right as well. Okay, next point. Movement data don't provide the answer. Here's a great quote from 1932 from the Journal of Bone and Joint Surgery. Empiricism fostered by trial and error must continue to govern the therapy of abnormal function until measurement in some form improves the treatment of disabilities affecting the back and lower extremities. Okay, let me boil that down to one phrase. If we can measure it, we can fix it. Right? That was the perspective back in 1932. Well, we can measure a lot of stuff today, so this is a data collection session from the Knee Grand Challenge that Tor and I were involved with. So we can measure ground reaction forces using force plates under subjects as they walk. We can put markers on subject, and now IMUs. We're getting closer to being able to measure motion as people walk around with markers or IMUs in the gait lab. We can put electrodes on people and measure electrical activity in their muscles. In some cases, we can even use fine wire electrodes and get electrical activity out of deep muscles. So we have all of these data. We can back calculate how the person moved. We can calculate their joint moments. We can use more complicated models and estimate muscle forces and estimate contact forces. There's all this great stuff we can do. How has it changed clinical practice? Apart from treatment of cerebral palsy, where doctors do tend to look at gait data, but even then, it's very subjective, really hasn't changed clinical practice very much. So Dick Brand, one of the fathers of present-day biomechanics, had this great quote. He said, although locomotion analysis or gait analysis has always held great promise to aid the clinician, it has never lived up to its promise. Right? So that 1932 quote wasn't true. Just because we can measure it doesn't mean that we can fix it. So what's the problem? Well, movement data tell us what a patient does, at least externally, but unfortunately, it doesn't tell us how to fix the patient's problem. It can be a good part of the process, but there's still something lacking. And finally, people change over time. Despite powerful investigational tools, I would argue biomechanics, again this is from Dick Brand, I would argue biomechanics has made a relatively minor impact in clinical practice, primarily because most studies fail to account for the major distinction between living and non-living systems, adaptability. While any study requires a clear question or hypothesis or goal, without accounting for adaptability, these studies might well be termed necromechanical, right? Necro for dead. So really, if you think about most of the research that most of us do, we'd probably say that our biomechanical research is actually necromechanical in nature because nothing is changing, nothing is adapting, key characteristic of living systems. And that's important for neurorehabilitation because our brains need to change and adapt to help people recover. All right, so those are some of the challenges. If we want to design treatments with walking models, what ingredients or what elements are we going to need to have? And I propose that we need 3 elements. We need a clinical measure, we need a problem that matches certain clinical requirements, and we need a clinical model. So let's look at each of those. So first, a clinical measure. Again, another quote from Dick Brand. The acid tests of clinical usefulness of any measure, any quantity that we might want to assess clinically, are whether that measure predicts a different outcome than would be predicted without the measure, or whether the measure suggests a different treatment or a different implementation of the same treatment than would be recommended without the measure. Okay, so really what this clinical measure boils down to is a quantifiable target. It's something that we want to hit. It's a desirable value of a clinical measure, and it defines a target that we want to hit through treatment. So if you treat the person and you measure this thing after treatment, and that value reaches some value that you wanted to reach, you can say, aha, objectively, we were successful. So to be useful for designing optimal neurorehabilitation treatments, a clinical measure must be a reliable predictor of an individual patient's treatment outcome, and it must also be reliably predicted for individual patients using a computational walking model, where the word reliable here needs to be defined based on the clinical problem under consideration. So let me give you a couple quick examples to help solidify this a little bit. So for knee osteoarthritis, if you have osteoarthritis in the medial compartment of the knee, the peak medial contact force or the knee adduction moment might be quantifiable quantities that you could use to determine whether or not you've had successful treatment. So here's an x-ray of an individual with medial knee contact force, and you can see that there is no space left between the femur and the tibia, so all the cartilage is eroded there. Presumably the contact force on the medial side of the knee is much larger than the contact force on the lateral side. That's what our research has told us so far. Now, one of the challenges here, of course, is we can't measure contact force in people's knees. We'd have to cut you open and put a sensor in there, and the ethics committees may not let us do that, and it might damage your joint surfaces more, so we don't want to really do that. So we want to have some external measure that's a good indicator of medial contact force. And a lot of research has pointed to the idea of the knee adduction moment being such a measure. So when you walk, your foot exerts a force on the floor, the force exerts a force back in your foot, it points up toward your center of mass. there is a distance between that ground reaction force vector and your knee center, so that gives you a moment arm. A force in a moment arm is a moment, so the moment of the ground reaction force vector about the knee center is the knee adduction moment. And that has been shown to be, under certain conditions, a reasonable indicator of medial contact force in the knee. So that could be a clinical measure, and in fact, work that Tor has done and work that I have done, we've both tried to target that knee adduction moment measure to treat knee osteoarthritis. If you want to think about stroke or Parkinson's disease, the situation's even easier. What do people want to improve if you've had a stroke? The main thing they want to do is walk faster. And then the next thing they want to do is they want to walk in a more normal fashion, which means they want to be more symmetric. And so walking speed and symmetry are things that are very easy to measure in a gait lab. So those are good clinical measures. All right, clinical requirements. So if we want to use a computational walking model to design neurorehabilitation treatments, then there are 5 requirements that the clinical problem needs to have. First, the walking impairment should be influenced heavily by patient-specific factors, such as unique patient neurological, physiological, or anatomical characteristics. So basically what that means is cookie-cutter treatments aren't going to work very well because it's so unique to the patient. Second, standard treatment approaches should be either ineffective or inconsistent at restoring normal walking function. Again, if standard treatment approaches work well, no need for pulling out the big guns and trying to make computational models of patients. A clinical measure can be identified, that can quantify the initial clinical state and the final treatment outcome. So we need to have that target that we want to hit. Clinical treatment parameters can be identified that can be changed. That's our prescription and dosage, and are likely to affect the clinical measure. So we need to know what knobs can the clinician turn to try to help the patient get better. And finally, the clinical measure can be measured in the lab before treatment, so we know where we start. It can be predicted with a computational walking model. That's how we design the treatment. And then finally, it can be measured again in the lab following the treatment, so we know whether or not the treatment actually worked. And finally, the clinical model, right? So we're going to have a model at the core of this process that we're going to use to try to predict how to treat the patient. So to be useful for neurorehabilitation treatment design, a computational walking model should have 3 characteristics. It should be predictive, capable of predicting how the clinical measure will change in response to a proposed treatment prescription and dosage. It should be minimally complex, containing only those model elements necessary to predict the clinical measure reliably for an individual patient. And it should be patient-specific, capable of having relevant model parameter values calibrated to the patient's pre-treatment walking and other data. So these things are all pretty intuitive, right? We don't want to make models that have complexities that don't help us solve our problem. Of course, it's got to be patient-specific if we want to design treatments for patients, and of course, it needs to be able to predict what's going to happen if certain treatments are applied to the patient. All right, so we've looked at the challenges that we have to doing treatment design with computational walking models. We've looked at the ingredients that we need if we want to try to do this. So next question, what treatments have already been designed using patient-specific computational walking models? Well, the answer is not many. So this is an area where we really, despite all the analyses that we've done, if you look at actual treatment design for individual patients, there's very, very little that's been done. Apart from an example that I'm going to show you from work that we've done, the only other thing that I know of is a treatment designed for individuals who have diabetes and have ulcers on their feet, done by Ton Vandenboger at Cleveland. So a lot of room here for growth. So we're going to look at an example related to knee osteoarthritis neurorehabilitation. So this is work that was primarily done by Jeff Reinbold, who's now an assistant professor at the University of Tennessee. And it was originally funded by the Whitaker Foundation and the National Institutes of Health. So the problem, you've got knee pain and walking impairment due to knee osteoarthritis. So for those of you who aren't familiar with knee osteoarthritis, so in the knee we have our femur and our tibia bones. We have cartilage called articular cartilage that lines the end of the femur and the top of the tibia. And then we have 2 half-moon-shaped cartilage pads called the menisci that sit there between the 2 bones. And frequently when the meniscus is damaged, that causes stress concentrations between the femoral cartilage and the tibial cartilage. And eventually over time, could be from a torn anterior cruciate ligament as well. There are a number of things that can cause this to happen. But over time, the cartilage lining the ends of the bones can begin to erode. It becomes painful, movement becomes difficult, and then you have osteoarthritis. So the ingredients, we're going to look at a clinical measure. We're going to look at the clinical requirements for this problem, and we're going to talk about the clinical model. The approach we're going to use to address this is a patient-specific predictive walking optimization. And the results, we're going to see that a modified walking pattern is able to produce a significantly reduced clinical measure that the patient that this was designed for, I'll disclose early on, happened to be me, that it actually worked. And I'll just point out too, this is, as far as I know, this is the only treatment that was completely designed with the computational walking model without having a clinician predict beforehand what the treatment would be. So our clinical measure, I talked about this before, it's the peak knee adduction moment. So the ground reaction force vector has a distance to the knee center, so there's a moment. The larger that moment, the larger the medial contact force. And so this is what the knee adduction moment curve looks like over the walking cycle. This is heel strike. This is subsequent heel strike at the same foot on the ground. The y-axis here is normalized units of percent body weight times height. And this curve tends to have two peaks. One during early stance, as you're beginning to load your leg, and one during late stance as you're getting ready to unload the leg. If you look in the literature, you find that the magnitude, the peak value of this knee adduction moment curve predicts the rate of osteoarthritis progression. So if you have osteoarthritis, if you have really big peaks, you're probably going to progress faster. You have smaller peaks, you won't progress so fast. If you get what's called high tibial osteotomy surgery, so if you're bow-legged, that tends to put more weight on the inside of your knee. Doctors can go in and cut your tibia, make you knock-kneed, and presumably shift some of the contact load to the outside of the knee from the inside of the knee. And when they do that surgery, if you can get the peak value below about 2.5% body weight times height, then you tend to do very well in the long term. So certainly this knee adduction moment is related to clinical measures of osteoarthritis. Okay, for this problem, does it meet the 5 clinical requirements that I outlined? Well, this walking impairment is likely to be influenced heavily by your leg alignment, right? If you're bow-legged, it's going to be worse, and also just your general walking pattern. So it meets that requirement. Standard non-surgical treatment approaches are ineffective at relieving pain and restoring normal walking function, so it meets that one. As we just said, the peak knee adduction moment can potentially quantify both the initial clinical state and the final treatment outcome, so we have a good clinical measure we can use. The subject's walking motion can be modified, and it's likely to change the peak knee adduction moment, so satisfies the 4th requirement. And the 5th one, the peak knee adduction moment, can be measured in the lab before treatment. It can be predicted with a computational walking model to design the treatment, and it can be measured again in the lab following the treatment, so it meets the 5th requirement as well. So basically, this problem is worth pursuing with a computational walking model. So what should that model be? Well, the clinical model should, remember the first point, needs to be predictive. In this case, it needs to predict the patient's peak knee adduction moment for different modified walking motions. It should be minimally complex, which in this case, starting out, we're just going to use a skeletal model. We're not going to worry about the control strategy used by the patient's brain. We're not going to worry about how muscles are involved. We're just going to have torque actuators. We're not going to worry about details of how the foot interacts with the ground. We're just going to try to be as minimalistic as we can. And finally, in terms of being patient-specific, for this problem, the anatomy of the individual is going to be important. Again, if they're bow-legged or knock-kneed, that's going to influence things, and their mass distribution may be important. So we're going to calibrate those aspects of the model. So the objective here is to design a customized walking motion for a patient with medial knee osteoarthritis using a full-body, patient-specific computational walking model. And basically what we want to do here is we want to get the benefits of that high tibial osteotomy surgery, a very invasive surgery, but we want to do it simply by teaching someone how to walk differently. Wouldn't that be nice if we could get the benefits of a highly invasive surgery just by teaching someone to walk differently? All right, so the experimental data. We have a single subject with medial knee OA who looks a lot like me when I had less gray hair, walking at my self-selected speed of 1.4 meters per second. By the way, there's a really good history of biomechanists doing self-experimentation, so this is very on the up and up. So we had a 6-camera motion analysis system, 2 AMTI force plates in the ground to measure ground reaction forces, and the subject performed isolated joint motion trials to try to calibrate where the joints should go in the body segments, along with walking trials. So the model that we constructed, it's a 27-degree freedom model. So there are 27 independent translations and rotations that we need to define to specify the configuration of the model. It's three-dimensional. All the joints are engineering joints. So the hips are ball and socket joints, the knees are pin joints, the ankles are 2 non-intersecting pin joints, the back's a ball and socket joint, the shoulders were universal joints, and the elbows were pin joints. And we developed the equations of motion for this model in a symbol manipulation program called AutoLab. So we calibrated the positions and orientations of the joint axes in the lower body. And in this animation, you can see what the calibrated results look like. The blue circles are markers on the subject, and the red dots are corresponding markers on the model that we created, the skeletal model. And you can see there that the model, which has joint constraints in it, is able to follow the experimental marker motion very closely once we put all the joints in the right positions. And we also calibrated the mass distribution of the model because we felt that the mass distribution may be important. And all of these approaches are things that we've published previously. All right, so now that we have the model all set up, what we want to do is predict how the subject should walk differently to reduce the peak knee adduction moment. And this was the first attempt at the prediction, and as you can see, it was an abysmal failure. So why was this first prediction an abysmal failure? Basically because we tried to do it using forward dynamic methods. So when you do forward dynamic optimization, you guess controls, in this case joint torques that would control the legs and upper body. And then you simulate a motion using a forward dynamic simulation. You time march forward in time. And of course, our human bodies are big multi-segment inverted pendulums, so we're totally unstable. There's no feedback control in this model, and so it just falls over terribly. So that approach didn't work very well, and I really didn't want to get into creating all sorts of fake feedback controllers just to keep the model up that may not represent what the person's actually doing. And so we decided to use an alternate approach. So our requirements is we want to have stable simulations. If the model falls over, we're not going to be able to optimize it. We wanted them to be fast, a matter of minutes rather than hours or days. We didn't want to have a complicated ground contact model for this first implementation, but we did want it to predict realistic looking walking motions. So some of you have seen the Ministry of Silly Walks Monty Python video, right? If I had some crazy walking motion like this and it was good for my knee, no one would do that. So we wanted to come up with a walking motion that would be realistic looking. And so we made some concessions. Instead of doing forward dynamic optimization, we decided to use inverse dynamic optimization, which in this case meant that we would guess joint motions and then back calculate what the joint torques would be that would be required to create those motions. Now there's one downside to doing inverse dynamic optimization with that approach, and that's that when you calculate the joint torques, you also get some fake forces and torques that are acting on the root segment, the segment connected to ground, which in our case was the pelvis. So what that meant is every time we did an inverse dynamics analysis, we got 3 extra forces and torques acting on the pelvis, which was kind of like the model's walking around and someone's grabbing the pelvis as it's going, which is not very realistic, but it's a price that we had to pay for this approach. So we try to keep those low. We constrained the path of the foot through space. We didn't want to have a ground contact model. So we said however the feet moved through space originally, then we're just going to force them to follow the same path through space. So what you can do upstream of the body can change, but the way the feet move can't change. We took the experimental ground reaction data and just applied it to those feet. We let the ground reaction data change a little bit under the feet, but we made sure that the center of pressure stayed under the foot, so we didn't really have a ground contact model. And then in addition to minimizing the knee adduction moment, we also minimized control torque changes. So the assumption there is we want to find a new walking motion that looks normal, that uses more or less the same leg control torques as the patient's original walking motion. The assumption being that those torque changes would be similar to minimal neural control changes. All right, so here's the experiment, the experimental motion at the point with the largest adduction moment. And you can see there's a good sized moment arm there. And here is the optimization prediction. You can see there's less black space, so it reduced the moment arm to reduce the moment. And if you look at the 2 walking motions side by side, they look pretty darn similar. So the optimization was successful. It predicted a new walking motion that looks more or less like the subject's original walking motion. And as we'll see in a second, it produces a huge reduction in the peak knee adduction moment. And at this point, people usually ask, well, what in the world is it doing? How did it do that? And it's one of those things where after the fact you go, duh, that was so easy. But no one ever thought of it. The model had to figure it out. So basically what the model predicted is that the name of the game is you want to reduce the moment arm here. And to reduce that moment arm, either you can tilt out to the side, and you'll see this next time you're walking around in downtown Auckland. You may notice some people that are walking around like this. Well, they probably have hip or knee arthritis, and they've already figured out that by moving the center of mass laterally, they can reduce the moment arm about the joint and reduce the adduction moment. So people just figure that out on their own, but we don't want that sort of walking motion. So if you're not going to vault over on one side, what the model predicted is that if you stand and your knees are straight, you can't move them in very much to decrease the moment arm. But if you flex your knees just a little bit, look at that. Just the way the anatomy works, if with a little bit of flexion, you can now medialize your knees. So the model predicted that as you begin to weight bear, just flex your knee a little bit more than you would before, and now you can medialize, bring your knee toward the midline of your body, and you can cut down that moment arm. Very simple idea. But again, no clinician ever thought of it. It was predicted by the model. So here is the knee adduction moment curve originally. There's that 2.5% body weight times height target that we want to hit. Here's what the model predicted would be achievable, 32 and 34% reductions in those two peaks. So I went out and tried to teach myself how to do this, and then went back in the gait lab to see whether or not it would really work. And that blue curve is what happened after I taught myself how to do it. Got 39 and 37% reduction, so just about what the model predicted would be possible. So we published this in IEEE Transactions in Biomedical Engineering, and so that's a great start. Now the tricky part is, how do you teach other people to do that? And Tor's doing some work in that area. We've tried to do some work. The bottom line there is it's not so easy. So we can predict new treatments, but then the question is, how do we get people to do them? So that's the next step in the process. So this approach worked well for this application, but it has a bunch of limitations. So first, we completely ignored neural control factors. Not so bad for this application maybe, but what if you want to model people who've had a stroke? That's not going to fly. So if you want to do Parkinson's disease or stroke, you're going to have some sort of patient-specific neural control model. We didn't model any muscles. So as soon as you add in a neural control model that's controlling the muscle activations, you're going to have individual muscles in your model. And a good way to calibrate activation or EMG-driven models is to use an EMG-driven modeling process that connects EMG to muscle force. So that's another element that we'll need to put in. We couldn't accommodate large changes in foot path. Remember, we said we had to know the way that the feet move through the room. And of course, if you can imagine if you have cerebral palsy and your toes are pointed in, you might want to correct that and have a more normal foot strike pattern. Or if you've had a stroke and you're favoring one side, you're asymmetrical, you want to make that symmetric, your ground contact pattern is going to change. So if we want to model those situations, we need foot-ground contact models. And then finally, we violated the one thing that we have high confidence in. The thing we have the most confidence in this process is Newton, right? F equals ma. We're really sure about Newton, and it's one of the things that we violated here. And so we'd like to not violate Newton. We'd like our models to be dynamically consistent when we're done. So basically, the results of that modeling process then became the goal of my lab for basically the last 9 years, trying to say, how do we get all of this work to the next level where we can now bring all of these factors into the picture and model more complicated situations. And so the last point I want to talk about is what directions should be pursued in the future if we want to use computational walking models to design treatments for stroke, Parkinson's disease, cerebral palsy. And so what I'm going to do is I'm going to give you a stroke neurorehabilitation example for this last part, but I want to emphasize up front that this is work that is still under construction. I'm going to show you some results that we just generated literally last month to finish up one of my students' PhD dissertations. So we're making good progress on it. I think you'll get a good sense for where it's going. I think it's a pretty exciting area, and we'll see how all these different elements come together. All right, so for the stroke example, this is funded mainly by the National Science Foundation, and this involves elements of work that were done by Jennifer Jackson, who's now working at the National Institutes of Health, and Andrew Meyer, who is a consultant for a startup company that we're starting that doesn't have a name yet, so I can't give you the name of the company. So the stroke example, what's the problem? So hemiparetic walking impairment due to stroke. So one side of the body is affected, Don't let that fool you. The other side is affected as well because typically it compensates. So while the other side may seem normal, the interaction between the two sides is not normal because of the affected side due to the stroke. We're going to look at the clinical measures that we have for this problem, the clinical requirements to see if they're satisfied, and then what we need to have in the clinical model. We're going to talk about the approach, which again will be a patient-specific predictive walking optimization. And the results, for now, we're just going to look at predicting how will this patient walk faster. Why are we doing that? Because we can measure it and use it to evaluate our predictions. We don't want to start out predicting treatments right off the bat. First thing we want to do is predict some situation where we can evaluate whether or not our model is doing a good job. Ultimately, though, we want to be able to predict what is the best achievable walking pattern that a patient with a stroke can achieve given that individual's neurological limitations and remaining capabilities. And then what treatment can we use to get the patient there? So the clinical measure, we're going to use walking speed and symmetry. And this is a video of the subject who we're actually going to study. And this subject's self-selected walking speed was 0.5 meters per second. A healthy individual might be 1.2 to 1.4 meters per second. So less than half of a healthy individual's normal walking speed. So we want to improve speed and symmetry. The clinical requirements, are they met by this problem? Well, certainly the walking impairment is heavily influenced by patient-specific neurological factors, so that works. Standard neurorehabilitation treatment approaches are ineffective at restoring normal walking function. So if someone's had a stroke, they're walking significantly impaired, the likelihood of them getting back to full function is not great. Walking speed and symmetry can be used to quantify the initial clinical state of the patient as well as the final treatment outcome, so that's good. The subject's neural control strategy can potentially be modified and will change the subject's walking speed and symmetry. So there's something we can change, which of course brings up the issue of how in the world are we going to model the patient's neural control strategy, so we'll get to that in a second. And then finally, walking speed and symmetry can be measured in the lab prior to treatment. We can predict them with a computational walking model to design the treatment, and then we can measure them again in the lab following a treatment. So all 5 of those requirements are met by this problem. And finally, the model. The clinical model for this problem should be predictive. It should predict changes in the patient's walking speed and symmetry that are produced by predicted changes in the patient's neural control strategy. It should include neural control, muscle and foot ground contact models to create a minimally complex model. So in this case, the minimally complex model is going to have a lot more features in it than the previous model that we had for knee osteoarthritis. These are just going to be important elements if we want to predict how a stroke patient is going to walk differently. And it should have calibrated neural control, muscle, skeletal, and foot ground contact models to create a patient-specific model. So you can see that the complexity level of this model is significantly greater than what we had in the previous example. So the objective for this last part of the talk is to predict how an individual who has had a stroke will walk at a faster speed given experimental data for how he walks at his self-selected speed. So in this case, we've measured how he walked at both 0.5 and 0.8 meters per second, as I'll note in a second. We want to use the data from 0.5 meters per second to calibrate a model and then predict how he's going to walk at 0.8 meters per second, and then we can evaluate the prediction because we happen to have the data. So we want to evaluate how well our latest computational modeling approach can predict a stroke patient's walking pattern for a novel situation, which is walking faster in this case. So our experimental data collection, we had a single high-functioning stroke subject. He walked at 0.5 meters per second, which was his self-selected speed, and he also walked at 0.8 meters per second, which is fastest comfortable walking speed. We collected about 40 gait cycles for each speed. We had a 12-camera Vicon motion capture system and a Vertex split belt instrumented treadmill, which made it easy to collect lots of walking cycles. And one of the really unique things about what we did here is we collected EMG data, including some fine wire EMG data from 16 muscles per leg. So we have the iliopsoas, powerful hip flexor muscle, really critical muscle to model. Usually can't get that one because it's deep below other muscles. And we also have tibialis posterior, an important ankle muscle that's also deep. So we're going to need a bunch of elements in order to make this model work. And this brings up an issue in our field, which I call siloed research. A lot of times what we do in the musculoskeletal modeling world, or really, and this can apply to any research area, is people like to stay in their own niche. And each of these silos represents a different research niche. And one of the challenges that we all have as researchers is we need to learn when we need to cross the barriers between the different silos and how to combine the different silos. Just because we know how to work in one area doesn't mean we know how to work in the other area. And even if you know how to work in both areas, it doesn't mean you know how to make those areas work together. And so the different silos that we're going to need to cross here, we're going to use muscle synergy analysis as a way to do neural control modeling. We're going to have EMG-driven modeling as a way to model individual muscle function. We're going to have traditional musculoskeletal modeling with foot-ground contact modeling. And finally, we're going to have predictive gait optimization. And if you look at these 4 different areas, lots of times people will just stay within one. Some of them tend to cross boundaries a bit more than others. EMG-driven modeling and musculoskeletal modeling tend to go together. You'll see a decent amount of research in the literature where people combine musculoskeletal modeling and predictive gait optimization. You'll also see some work where people are beginning to combine muscle synergy analysis with EMG-driven modeling. That's just starting. But as far as I know, there aren't any studies to date that have crossed all of those boundaries between all of these different areas to put them into one predictive walking optimization paradigm. And so that's what we need to do to address this problem. So again, if you think of the different areas that we need, we said we needed patient-specific neurological models. The synergy analysis will do that for us. We need physiological models. The EMG-driven modeling will provide that. Anatomical models, we get that from the musculoskeletal part. And we're going to use direct collocation optimal control as a way to do our optimizations. So I'm going to talk about each of these 4 areas to finish up. So muscle synergy analysis. So here are 5 hypothetical EMG signals. And here are 3 hypothetical time-varying curves that could be used to reconstruct these 5 signals. And the name of the game for muscle synergy analysis is dimensionality reduction. So these 5 signals, according to synergy analysis, are not really independent from one another. They can be constructed from some smaller subset of signals or basis functions. And so we can take this first signal and we can give it a weight and then use it to contribute to this real EMG signal. We take this command, give it a weight, have it contribute here. So this one command is going to contribute to each of these 5 EMG signals based on 5 different weights. The same thing will be true for the second command and also for the third command. And so we can reconstruct these 5 signals given linear combinations of those 3 signals. We're going to call the time-varying signals at the top synergy commands. Those are our basis functions. We're going to call each of these weights a synergy vector. And a single synergy command and synergy vector together we're going to call a muscle synergy. And so the main idea again is that EMG signals that we can measure, they're not mutually independent from one another, but they can be constructed from a small number of synergy commands. And if you want to read more about this, there's a good Timish Fatal article in 2010 that describes it in more detail. So I'll just show you a quick example. So here's some processed EMG signals from walking on a treadmill. So we have lots of cycles here from 12 different muscles. The solid line is the average processed EMG signal. The dashed line is the standard deviation. And we can now perform synergy analysis on these 12 signals and try to reduce them down to some smaller dimensional subset. And as we do that, we first assume one synergy. And when we look at one synergy, we can come up with the one time varying signal and associated weights that will best fit those 12 signals. And we can look at how much of the variability in the 12 signals is accounted for by that one signal. And here it's about 70% in this data set. Then because it's a nonlinear operation, we have to throw that one away and then start over and go to 2 signals. And how much of the variability can we account if we had 2 time varying signals? Oh, now we're up to about 87%. What if we had 3? Oh, 92%. What if we had 4? Ooh, 95%. And of course, to get up to 100% of the variability accounted for, we would have to have 12 synergies. But you can see once I get above 4 and I'm above 95% of the variability accounted for, things get pretty flat. I'm probably fitting mainly noise out there. So really, most of the variability in this data set I can account for with only 4 time varying signals. That's pretty cool. And so here's what those time varying signals look like. And each of those signals has a set of weights that goes with it. So gluteus maximus, if I wanted to reconstruct that signal, I take this time varying signal times that weight, plus that signal times that weight, plus that signal times that weight, plus that signal times that weight, and I could reconstruct the gluteus maximus signal. And we can do that for all 12 muscles. And so the point here is that synergies can be viewed as modifiable constraints on a patient's neural control strategy. When we walk around, we just don't use any combination of 12 muscle EMG signals. We use some limited subset that can be defined in this lower dimensional space. Well, why do we care about that for stroke? Well, stroke reduces the number of synergies in the affected leg. So if you had 5 or 4 synergies originally, after someone's had a stroke, they might have 4 or 3 instead. Stroke changes the synergy vectors, but not the synergy commands in the affected leg. So the time-varying signals tend to be more or less the same after someone's had a stroke, but the coupling between muscle excitations defined by the synergy vectors tends to change. And what happens if you get neuro rehab? So stroke neurorehabilitation can change the synergy commands. Patients tend to change the time-varying signals, and in some cases, they're actually able to regain a larger number of synergies like they had originally before the stroke. So here's a nice quote about this whole perspective from Yuri Ivanenko, who's a big synergy researcher. The robustness of muscle synergies observed post-stroke supports the notion that descending cortical from the brain signals represent neural drives that select, activate, and flexibly combine muscle synergies specified by networks in the spinal cord and or brainstem. We don't really know where these things live in our nervous system. Could be in the brain, could be in the spinal cord. And suggest an approach to stroke rehabilitation by focusing on those synergies with altered activations, what I call synergy commands, after stroke. So basically what he's saying is, you know what, the things that seem to be changeable are the time-varying signals, consistent with another study. And if we can figure out how to get people to change those time-varying signals, assuming that the synergy vectors can't be changed, that might be a good way to improve stroke rehabilitation. So as a starting point for our model, we're going to assume that we're going to use muscle synergies as a sort of patient-specific neural control model, a very simple neural control model, and assume that stroke patients can change their synergy commands, but not their synergy vectors. All right, EMG-driven modeling. So this is really built on a lot of work that Tor did for his PhD dissertation and has continued to work on. So the whole idea behind EMG-driven modeling is that you have some experimental EMG data and you have some experimental joint motion data. You're going to put this into a box that first has an EMG to activation model in it. So you're going to change the EMG data into an intermediate quantity called activation. That activation is going to go into a muscle tendon model, which then is going to generate muscle force, which will then go into a musculoskeletal geometric model. And ultimately, all the muscles together are going to produce some muscle moments, which you want to compare with the moments you get from inverse dynamics. So the name of the game here is all of the modeling elements in this box have parameter values associated with them. And we want to turn those knobs through optimization until we can put this experimental information in at the top, and then the joint moments we get out at the bottom will match the experimental joint moments. So again, this is work that was pioneered by Tor with his advisor David Lloyd all the way back in 2003. Make you feel old. Man. And in our case, so we have 16 EMG signals for each leg, and we're going to apply those signals to 35 muscles per leg. So some muscles don't have an EMG signal, some muscles are split up into multiple heads, and if a muscle doesn't have a signal, we're going to take an associated muscle that's close by anatomically. Gluteus maximus, for example, gets split up into 3 heads in our model, so we'll just use its one signal 3 times, and we'll weight it differently as well. So the EMG to activation model, basically what we do is process the EMG data to get an EMG envelope, and then we have a time shift. There's a time delay in the model. And we don't really know what the amplitude of the EMG data is. The maximal voluntary contraction really isn't the maximal amplitude of the EMG signal. So we're going to have a free scaling for amplitude in our model. And then we're going to go through our first order ordinary differential equation that defines a dynamic property of activation, an activation dynamics model. And finally, we have a nonlinearization that changes our neural activation into a muscle activation that goes into the muscle model. And so we have different parameters in these models. We have a time delay, which we're going to adjust with our optimization process. We have a scale factor that we're going to adjust. We have an activation time constant we'll adjust. And we have a nonlinearization term that we adjust as well. And then in our muscle tendon model, this is what people call a basic hill-type muscle model. It says the force produced by the muscle is a function of the maximum force it can produce times part of the muscle that depends on the activation being sent to the muscle, and that activation gets scaled by muscle force length and force velocity properties. And then we also have some passive force generation by muscle, and then muscle inserts into a tendon at an angle called a tenation angle. And so this is a geometric property. And on these curves, we have, this blue curve is our active force as a function of normalized length in the muscle. The red curve is passive force as a function of normalized length. And then we also have a force velocity curve, so the way muscle generates force varies based on its normalized velocity. The inputs to this model that are time varying are the activation that we get from our activation dynamics model, the muscle tendon length and velocity, which we get from a geometric model. We have 5 parameters for every muscle, and if we assume a constant pronation angle, then we can get the normalized length and velocity that we need to operate on these curves down here. So the 2 parameters that we adjust in our model are the optimal fiber length, that's the length of the muscle at which it generates the most force, and the slack length of the tendon. And then finally, we have a geometric model. So in order to get moments, we need a moment arm R. In order to get muscle force, we need the muscle tendon length and the muscle tendon velocity. So the muscle tendon velocity is just the first time derivative of the length, and the moment arm is the negative partial derivative of the muscle tendon length with respect to the span joint angle. And we can come up with a similar relationship if there are multiple degrees of freedom that are crossed. And so the thing to note here is that VMT and R are functions of LMT. So we take advantage of that, and just from the literature, we parameterize LMT as a cubic function of the span joint angles, so theta cubed. And once we have that, we can basically get VMT and R for free. So that's really nice. And then what we do is these coefficients in our LMT expression, we basically make those free design variables in our optimization and add some constraints along the way to make sure that things cannot get unphysiological or non-anatomic. So this is the optimization process we follow to calibrate the model. I'm not going to go into details. Just know there's a big, hairy optimization process that we use. And here are some of the results. So what I'm showing you here, we have the left leg and the right leg. I forget which one is the predic leg and which is I believe this is the predic leg and this is the non-predic leg. I'm pretty sure that's the case. In any case, the black curves are the inverse dynamic experimental results. The red curve is where we don't do the geometric adjustments and calibrate the model, and the blue curves are where we do the geometric adjustments. And what we fitted here are the hip flexion extension moment, the hip abduction moment, the knee flexion extension, ankle plantar dorsiflexion, and ankle inversion eversion moments. We did not fit the hip internal external rotation moment. We just found that our muscles didn't pull in the right directions to be able to fit that moment very well. So we just had that as a torque control in our models. And bottom line here is we calibrated this model using data from 0.5 meters per second. We're predicting moments for the subject's walking data at 0.8 meters per second, and it does a really good job overall. And you'll see, especially at the hip, overall, with geometric adjustments, tends to do a better job at predicting the hip moments, apart from this spot right there, than the model without the geometric adjustments. So we now have a model for this subject where I can stick EMG data in and stick joint angle information in and joint velocities, and I can get out muscle forces and joint moments. So this is now a nice EMG-driven model. Okay, musculoskeletal modeling. So for this part, we just took a standard 29 degree of freedom open sim full body walking model. We scaled it to the subject. We went through the same calibration process for all the lower body joints that we did previously. And we also added a 2-segment deformable foot ground contact model. So for each foot in the model, we have a hind foot segment and a toe segment, and we have a bunch of springs spread across the bottom of the shoe. What we do is during the testing, we outline the shape of the shoe with a marker wand so that we know where the shoe is relative to the markers on the foot. And we use functions that are continuous and differentiable to describe the normal and the frictional forces under the shoe. And we go through a whole calibration process so that all the stiffness and damping parameter values and frictional parameter values in this model are calibrated to match the subject's ground reaction forces. And we use Adidas Sambas for this purpose, mainly because the sole is neutral and it's much easier to model that way. All right, so now we got all the elements. We're finally to the best part. How do we put all the elements in the hopper, mix them together, and actually predict something useful? And so again, what we want to say is how do we predict how our stroke subject will walk at 0.8 meters per second, given data for how he walks at 0.5 meters per second. And the approach we're going to use is something called direct collocation optimal control. And we're going to use some software to do that called GPOPS2. It works in MATLAB. and it was actually developed by my optimal control collaborator at the University of Florida, Neil Rao. So there are two main methods that people typically use for predicting new motion if you use a forward dynamics method. The first method is called the shooting method. So if you do a shooting method, you guess the controls in your problem, then you numerically integrate your motion forward, and you do that sequentially, and then you get a new motion, then you go back and you guess new controls, simulate forward again, repeat that process over and over. So strength is you end up with dynamically consistent motions. You don't have any residual loads like you do with an inverse method. But weakness is you have to numerically integrate, so you get integration drift. You can have a high integration cost. And like I said before, there are stability problems. The model's going to probably fall over, so you're going to have to do some sort of feedback control. So what do direct collocation methods do differently? Well, instead of just guessing the controls, they guess the controls and the motion simultaneously. So it's almost like a forward and inverse method combined. And then the dynamics are discretized across all the time points. And then the optimizer iterates guesses for both the controls and the motion at the same time. And it solves for all the time frames simultaneously. So there's no forward time marching that goes on. So the strengths were again dynamically consistent, but now we have no actual numerical integration. The integration process is actually built into the optimization process. And because we solve for all time frames simultaneously, guess what? Our models don't fall over. So I don't need to come up with cheesy feedback controls to keep the model up. So I really like that aspect. Of course, there's no free lunch. The price that we pay, you get a much larger number of design variables, so you have a higher optimization cost. So it makes it a little bit harder to get a good initial guess so that you can get a good solution. All right, so what we're going to do is take this direct collocation optimal control approach, and we're going to first calibrate a walking model at 0.5 meters per second, and then we're going to predict how the patient's going to walk at 0.8 based on what we got from our calibration. So using the data at 0.5 meters per second, we're going to do a big tracking optimization problem. I call this dynamically consistent synergy analysis. Normally when people do muscle synergy analysis, they just do it on the EMG data. We're going to do synergy analysis on the EMG data after it's gone through activation dynamics, but we're also at the same time going to try to match the ground reaction forces, the lower body joint torques from inverse dynamics, and the upper body joint motions. So we're essentially going to match the whole walking motion with one optimization. The constraints, we have to satisfy the skeletal dynamics, and we want to produce a near periodic motion. And what are the design variables or the knobs that we're going to change? We're going to have 5 time varying synergy commands per leg, and we're also going to have the associated 5 synergy vectors per leg. So we're finding the same stuff that we would find with a normal synergy analysis, except now those synergies are actually controlling muscles that are controlling a walking motion. And we're also going to vary the initial conditions. Once we have that solution, we're going to repeat a very similar problem, except we're going to do it for 0.8 meters per second. So we're just going to speed up the treadmill belt in the model, and we're going to fix different final times and then predict how he walks for different given final times. And what we're going to assume here is that the synergy command, or excuse me, the synergy vectors are now going to be fixed, but we're going to vary the synergy commands. So the time varying synergy commands, we're going to assume that the subject can change, which was consistent with what we saw in the literature. And we're going to assume that when the subject walks faster, he tries not to change the synergy commands too much. So find a new solution where all the subject does is tweak the synergy commands a little bit in order to walk faster, still satisfy the skeletal dynamics, still produce a near periodic motion. The upper body is a bit of a problem. All we do is we track the joint motions from 0.5 meters per second there. So just assume he doesn't change his arm motion too much. Okay, so those are the two problems. So how did the calibration problem do? So here's the experimental motion. Here's the calibrated motion that we get with our synergy controlled model. And they're essentially identical. If you looked at all the plots, they're like everything's on top of each other. So we can calibrate this model and get it to reproduce the experimental walking motion from the trial that we're using at 0.5 meters per second extremely well. Okay, so now that we have this model, we're going to lock down the synergy vectors, let the optimizer change the synergy commands, and predict how the model is going to walk at 0.8 meters per second. So before I animate it, just note a couple things. If you look at the ground reaction force vector at this point in the cycle, or at the start, you'll see in the right foot it's a bit too high here. That's the only part of the cycle where it's off. It's great the rest of the time. And you'll see the arms are quite different. We commented on the subject when he walked faster, we said he was kind of strutting. He was kind of like going like this. And one of the things that we've learned from the model is that you can do a lot with your arms that doesn't really affect your legs that much. So we just don't think it's very sensitive to the arms. But you'll notice the starting configurations of the legs looks very similar. If we now look at the two motions, it's a really good prediction. The model does a really good job of predicting his leg motion and pelvis motion for how he's going to walk at 0.8 meters per second. If I showed you the plots, I don't have time, but it looks really good. Now here's an interesting question. What if I use torque controls instead of having muscles in there? I get rid of muscles, I just have torque actuators. Oh, by the way, so this is only 5 synergy commands per leg to produce the lower body motion. That's pretty cool. So now what if we put torque commands in? You'll notice the starting position of the legs doesn't turn out right. His left leg is going to take a much smaller step in order to try to not change the joint torques very much. So now when we look at this motion, it's still realistic looking, but it's nowhere as close to the actual motion as the synergy-driven optimization was. And in fact, if we run a bunch of optimizations with different final times, we haven't figured out how to make this work yet where we can let the final time be free and just have it be predicted. So what we do is we lock down the final time for fixed belt speed and then say, predict the walking motion, and then we looked at where the cost function was the lowest. And this little black dot here is for the gait trial that we used. So we would hope that if you try a bunch of different final times, the minimum would be close to this value, which it is for the synergy-driven model, but it's not for the torque-driven model. So this is just another indicator that the synergy-driven model is more realistic. So, all right, great. We can predict how the subject walks faster. We can do it very realistically for his lower body. What do we do next? So this is the point where we're starting to look forward. And really what we want to do is figure out what's the best achievable walking motion for this individual. If he had free ability to change his synergy commands, how fast could he walk and how symmetric could he get? So we want to figure out how to formulate that problem and solve it. We can start to look at some specific treatment things as well. For example, what if you could electrically stimulate one muscle? So you're just going to augment the EMG of one muscle anywhere in the gait cycle. Which muscle would you pick on his affected side and how would you stimulate it? What if you could do 2 muscles? We should be able to answer that question. I'm actually looking at that question with some researchers at Georgia Tech and Emory. Restoration. What if we wanted to predict minimal changes in his synergy commands to achieve a certain improvement in walking? Then we could look at how the EMG patterns would change and how the motion would change, and maybe we could come up with some sort of real-time feedback training scheme for the subject, maybe using inertial measurement techniques. Compensation. We might be able to come up with an exoskeleton orthosis design that would add extra torque just in the places in the cycle where the subject needs it, where his muscles aren't able to do it. And we could do something similar with what I call an assist, instead of assist as needed, I call it assist where needed, robotic gait training. So this person can do certain things with his muscles, he's got some gaps in his walking ability. What if you could get the robot to just fill in the gaps a little bit, and then gradually over time, you remove that assistance? Would that help the person learn how to fill the gaps in on his own? All right, so let me summarize to finish up. So muscle synergies may provide a simple way to model patient-specific neural control capabilities and limitations. Direct collocation optimal control is a promising approach for predicting a patient's achievable walking motion and potential ways to improve it. And future research should explore whether restoration, augmentation, and compensation treatments predicted by this methodology produce significant improvements in walking function following stroke. And of course, all this work is not done in a corner by myself, so I've got tons of collaborators, including one here at the University of Auckland, and a bunch of former students, current students that have contributed different aspects to this work. This is really the funnest part of the job, is all the great people that you get to work with. And of course, want to thank my funding agencies that have funded different aspects of this work, and thank Tor again for the invitation to come here and see your beautiful country. Got to visit the South Island this time, so you may recognize Franz Joseph Glacier there.
You got to see it before it goes.
I know, look how much it's received in the last couple of years. But anyway, that's all. Thank you very much.
Wow, time hasn't changed. It's still,
that was a fast presentation.
It's
still 8:02.
Time has stopped. We have time maybe for 1 or 2 quick questions before we have to open the drinks. Yeah, go ahead.
I would like to ask for the synergy weight and so the basis function and the weight.
I might miss it. Have you do a validation on that? So you have selected 12 signals to get your bases and your weights, but this 12 could be an outlier. So you segmenting. So basically, have you tested your basis function? Something like leave one out. Something like.
Oh, I see what you're asking. Yeah, so that's kind of a different. We have that's a related question, and here, stop. Put my glasses on. We have tested this approach, not within this modeling framework, but we did an interesting test where we asked the question. So we took some of these same data sets. We had a data set for me where I think we had 25 muscles on one leg, and then we had the data set from this subject with 16 muscles on both legs. And here we asked the question, what if you only had 8 surface EMG signals from muscles that people commonly use to collect surface EMG? And what if we extracted the basis functions from those 8 signals, and then tried to use those basis functions to construct all the other signals that we didn't use in the synergy analysis? So I call it synergy extrapolation, right? So we've got, for the stroke subject, we've got 8 muscles that weren't used in the synergy analysis. Can I take those basis functions and find weight so that I can reconstruct the other 8 muscles? And so here's my data, here's both legs of the stroke subject. The answer is yes, it works really well. So we have that going through review in the journal right now.
Yep, before Paul can get the last say.
So I was just asking on a related note here, can you actually predict the EMG signals from shape changes of the legs themselves, so tracking changes in the shape of the leg?
Yeah, I don't have any knowledge of how to do that, looking at how the leg shape changes. That would be some indication of, hey, the muscle's contracting,
yes,
and the force is changing, but I've not looked at that at all. Do you have any comments on that from,
I'd say
you haven't really done it dynamically, but
very hard, I would say.
yeah. Where's Jeff?
There's a lot of sliding too between the fascia and the surface of the skin.
Can Sylvia do anything like that? If you predict the change in the muscle volume, can that get related to either EMG or force somehow?
Well, yeah, I mean, it's related to both, right? Because if you get an EMG signal, that's great because you can understand the relative activation.
Mm-hmm.
But in terms of force, that relative activation needs to be scaled by the size of the muscle. And what we've been finding is from average healthy people are pretty similar in terms of muscle distribution, but when you move to an athlete or someone with stroke, cerebral palsy, the distribution of muscles becomes very different across populations. So yeah, we advocate that should be a factor in all these modeling approaches as well.
Paul.
Why did you limit your validation to only one other, gait speed? I would imagine that as you move further away, either slower or faster from the 0.5 meters per second,
Right.
You'll start to get discrepancies.
Mm-hmm. Yeah, the farther you extrapolate, the more discrepancies you get. Well, 0.8 was as far as we could go, because that's as far as he could walk.
What about slower though?
So slower we could do down to 0.4, which isn't really much of a difference for him. But I will say that when you look at him walking slower, you hit a certain speed in walking where it actually gets harder to walk when you walk slower.
Sure.
And so we went for walking faster, mainly because clinically, what you want to do is get people to walk faster. You don't want to necessarily get them to walk slower clinically. Although who knows, that might have some value as well. So starting out, first thing that we did is we just said, can we get the model to walk faster and do it in a realistic fashion?
So you actually tried beyond 0.8 meters per second. We found that it didn't.
No, we did I think we did 1 meter per second. I can't remember what we found, but the reason, so we just wrote this up in a journal manuscript that's in review. The reason we didn't put it in is we had no basis for evaluating it. Like, it looked reasonable, but was it right? Was it not right? So what we wanted to do coming out of the chute is do a prediction where we could actually evaluate the prediction and say, is this a good prediction or not? And we had data for 0.8, and that was as fast as he could go, so we decided, okay, that's a prediction that we can evaluate. But you can see for the torque-driven one, it didn't do a very good job of predicting. Although it was still a realistic looking walking motion, it just wasn't what that person does at 0.8 meters per second.
So I've just told Paul he could have the last say, but of course Martin has to stick his hand up now.
Well,
I'll let you have one. Yeah, Paul will have another one after that.
Thanks, PJ. I was just I'm still thinking about these commands and the dimension reduction to deduce these commands. I guess where this might be heading would be perhaps some way of modifying those commands
Exactly.
to be able to change things.
Right, exactly.
But what I'm trying to get my head around is that, is there any reason to expect that these command functions should bear any resemblance to any sense of physiology?
That's a great question.
Because I'm wondering
Yeah,
about factors like redundancy in physiology. That cannot be a feature of these linearly independent commands. So if redundancy can't be there, then can we reasonably expect that these commands are physiologically modifiable?
Well, the one thing we can say is that there's been one study done so far where they took individuals who had a stroke and they trained them, and they did just straight synergy analysis, so none of the rest of the musculoskeletal modeling part, just EMG data. And they looked at the EMG data before and after treatment, and they said, what changed? And what they found is that the people that improved changed their time-varying basis functions, what I call the synergy commands, that they were able to modify those somewhat, and that the synergy vectors didn't really change. In some cases, what happens when you do these analyses, and there's an artificial aspect to this, is people define the number of synergies based on when they cross an arbitrary threshold for how much of the variability in the data is accounted for. People usually use 90 or 95%. So someone could be at 89% variability accounted for with 3 synergies, and you'd have to go up to 4 synergies to get 91%, and they would say, aha, this person has 4 synergies, right? So they only had 3 at 89. So one of the things that I think is happening is when they say someone gains a synergy, which basically means when you lose a synergy, what they find is that the weights or the synergy vectors get merged. So if you had 4, the synergy vectors you have 3 will be merged versions of what you had at 4. And then they claim that some people unmerge them after training, but what I think really is happening there is that person, for the same number of synergies, they went from 89% to 91% or something. There was a small change. But bottom line, there is at least one study that says people can change the time-varying neural commands in response to neurorehab, and there's another study that hypothesizes that as well. There's not really evidence right now that they can change the weights, but I think the jury's still out. It's all, looking at what happens with treatment is very new. Most of what's been done so far is, here's a healthy population, here's a clinical population, what's different between the two. And I think one of the challenges going forward is trying to figure out how can we use the synergy information, coupling it with the model of the subject to link the synergy information to function, which has not really been done very well, so that's one of the things we did here. But also understanding what in the world can that patient do? How can they change their synergies? If you think about it, a healthy person, we're using synergies too. Again, where do those come from? What do they represent physiologically? We don't really know. All we know is we can calculate them mathematically. But a healthy person operates in a big box. They can do lots of synergies. You have a stroke, your box gets reduced, but there's still space in that box. And so our assumption is there's probably some other space in that box where the person can walk better, and maybe they just haven't found it yet. And we want to see if we can find a way to help them find these corners of the box where they can walk better.
I think in the interest of time, we'll close it up there, and thank you again.